What specific problem does the MPMV2 method aim to solve in the context of high-energy physics, and why is this problem significant?
The MPMV2 method aims to address the challenge of effectively training foundation models, FMs, for high-energy physics, HEP, tasks, particularly in the context of particle jet reconstruction from unlabeled experimental data. This problem is significant because traditional supervised learning approaches rely on high-quality simulations that do not perfectly represent real data, leading to domain shifts and inefficiencies. MPMV2 enhances the training paradigm by improving model architecture and exploring alternative reconstruction tasks that eliminate the need for costly VQVAE-derived targets, thus allowing for more direct application to real experimental data. By focusing on self-supervised learning techniques, MPMV2 seeks to leverage the unlabeled nature of experimental data, which is abundant in HEP, to produce more robust and generalizable models for downstream tasks related to jet physics. This advancement is crucial for advancing research in fundamental physics, including studies of quantum chromodynamics and searches for new physics phenomena.
How does the MPMV2 algorithm work? Illustrate step by step, including the roles of the encoder, decoder, and the reconstruction tasks defined in the paper.
The MPMV2 algorithm operates through a series of steps involving an encoder, decoder, and multiple reconstruction tasks. First, the algorithm takes a set of particles representing a jet, where a random subset of these particles is masked. The encoder processes the remaining particles to produce a latent representation, which is then passed to the decoder. The decoder, designed as a smaller transformer, reconstructs the masked particles based on the latent representation, utilizing positional encoding only for the masked elements to maintain efficiency. The reconstruction tasks in MPMV2 are crucial for training the model effectively. These tasks include recovering the particle type classification, using a VQVAE-derived classification, direct regression of continuous features, k-means tokenized classification, and employing a conditional normalizing flow for generative modeling. Each task contributes a loss term that is summed during pre-training, allowing the model to learn rich representations of the particles while avoiding the inefficiencies and information loss associated with previous methods. This multitask approach enhances the model's performance and generalizability across various downstream tasks in jet physics.
Can you provide a clear, illustrative example of how MPMV2 predicts a missing particle feature using the reconstruction tasks? Walk through the procedure with hypothetical data.
In MPMV2, the prediction of a missing particle feature is achieved through a series of reconstruction tasks that utilize both continuous and categorical features of particles. For example, consider a hypothetical jet composed of 5 particles where the features of one particle, let's say its type, are masked. The model first identifies the remaining 4 particles and their features, which include kinematic attributes like energy and momentum, as well as the particle identity. During the reconstruction process, MPMV2 employs a classification task to predict the masked particle type by comparing the features of the known particles to the learned representations in the latent space. Specifically, it uses a linear layer with a cross-entropy loss function to classify the missing particle's identity based on the context provided by the other particles in the jet. This approach allows MPMV2 to effectively leverage the relationships among the particles to accurately infer the missing feature, demonstrating its capability to handle unordered sets without positional encoding.
What are the key theoretical or practical benefits of using MPMV2 compared to its predecessor MPMV1, particularly regarding the efficiency and performance of the model?
The key theoretical and practical benefits of using MPMV2 over MPMV1 include enhanced model architecture and improved efficiency in the training process. MPMV2 eliminates the redundancy of using identical masked tokens in the encoder, which allows for a more efficient computation by removing all masked tokens from the input set and reintroducing them only during decoding. This change reduces the cardinality of the latent representation, leading to a 40% reduction in GPU memory usage. Additionally, MPMV2 incorporates a more powerful transformer decoder, which significantly improves the accuracy of regression tasks, narrowing the performance gap between MPMV1 and MPMV2. Overall, these modifications result in a more performant model that can better handle the complexities of jet physics while being computationally efficient.
How was the effectiveness of MPMV2 validated in experiments? Discuss the datasets, benchmarking methods, and evaluation metrics used in the testing phase.
The effectiveness of MPMV2 was validated through a series of experiments using two datasets: a publicly available dataset containing 120 million large radius jets and a BTAG dataset with 3 million jets. The models were benchmarked against a randomly initialized network to highlight the performance improvements provided by pre-training. Evaluation metrics included classification accuracy, particularly in distribution tasks where the number of jets varied from 1,000 to 100 million, and weakly supervised classification using the principle of classification without labels, CWOLA, to assess performance with noisy or incomplete labels. The significance improvement, SIC, was also calculated for weakly supervised tasks, measuring the signal efficiency against background efficiency. Results showed that all pre-trained backbones outperformed the baseline, with the K-means backbone achieving the best performance with larger datasets, while the CNF backbone excelled in out-of-distribution tasks.
What specific results were achieved by MPMV2 on the downstream tasks, and how do these results demonstrate its advantages over traditional methods?
MPMV2 demonstrated significant improvements in downstream tasks compared to traditional methods, particularly in classification accuracy and data efficiency. For instance, when classifying jets, MPMV2 backbones achieved accuracies between 85.0% and 85.3% with 100 million jets, outperforming the randomly initialized network, which achieved only 84.3%. Notably, the K-means backbone excelled with larger datasets, while the conditional normalizing flow (CNF) and regression backbones exhibited greater data efficiency, achieving comparable performance with fewer jets. In weakly supervised classification scenarios, MPMV2's regression backbone achieved a signal efficiency improvement, SIC, of 8.18, showcasing its effectiveness in handling noisy or incomplete labels. Furthermore, MPMV2's generalizability was evidenced by its superior performance on the BTAG dataset, where all pre-trained backbones outperformed the benchmark, indicating that the learned representations are robust across different jet definitions and experimental settings.